Okay, hello everyone. First and foremost, thank you so much to Hofi, to Jake, to Nima, to Sebastian for bringing together this fantastic crowd. And I'm honored to be given the opportunity to speak here. So this is an attempt to review recent developments in string amplitudes, and I will follow the disclaimer of all the previous review speakers that this is going to be a highly personal and biased and incomplete account. So take everything that you see, including the choice of material, with a grain or maybe a bag of salt. Okay, so I should start with an attempt to get people enthusiastic why to look at string amplitudes at all. So first of all, there is some motivation from within string theory, starting with the fact that it was an amplitude who got the field started. And when it comes to string amplitudes in flat space-time, there is already one major motivation to compute them, as they tell us about the low-energy corrections beyond field theory. So the open string has super Young-Mills field theory in it, plus alpha prime corrections in certain higher derivative operators. And likewise, closed strings not only contain supergravity, but also augmented by infinite towers of such higher derivative operators. Yeah, and all of these alpha prime corrections have a very tight interplay with string dualities, opportunities to test and exploit them in various ways. And all of this already in flat background. So not surprisingly, the second bullet point is even more exciting. String amplitudes in ADS have a lot to say about gauge gravity duality, holography. There is very recently a very tight interplay with exact calculations in n=4 super Young-Mills with so-called integrated correlators. And I will shamelessly leave it to the next speaker, Tobias Hansen, to update you on this super impressive progress in the curved space-time story. So I will mostly restrict to flat background, where I hope I can convince you that there are also some yummies, also from the last year. Okay, so how do string amplitudes connect to what other people do in the room who don't identify as string theorists? So there is a lot of wisdom that can be exported from string amplitudes into adjacent fields. So here are two examples where this cross-fertilization is going particularly strong. String amplitudes have a lot to say about the perturbative double copy structure of gravity. So this BCJ color kinematics duality in gauge theory gives you a neat way to obtain gravitational amplitudes or their loop integrands from squaring. And both the color kinematics duality and that squaring prescription has a long history dating back to a string theory work from '86. And there are various tools how to enhance the understanding of double copy coming from strings. Yeah, this is intro example number one of a neighboring field which benefits. And then a second one, which I try to illustrate in the second half of my talk. String amplitudes help you a lot to study special functions that are relevant to Feynman integrals that you can in turn use for precision calculations in both particle physics and gravity. So I will try to illustrate how string amplitudes give you interesting numbers and functions in a very simple context. String amplitudes as a math laboratory to find multiple zeta values and polylogarithms on various geometries in a very inviting and simple setting. Yeah, as you can already see from these previous points, string theory is a good framework to offer formalisms for scattering amplitudes. There is a large number of formalisms that many people in the room have used and developed, which have a very strong synergy with string amplitudes. First in the list is the world line formalism, which has a history going back to the 90s when, for instance, the Bern-Kosovo rules came up and somehow kicked off many amplitudes developments. And more recently, the world line is coming back and playing a star role in gravitational precision calculations, thanks to the work from the Humboldt group and AEI. Then CHY and ambitwister strings. In 2013, all of this started, where Riemann surfaces came up. Initially, not really clear how to connect with conventional strings, but then all the nice work from the ambitwister gang led to a very beautiful web of limits and connections in between different string theories and field theories. Then next subject, tropical geometry. I firstly learned about this when Piotr Tokin has his seminal paper on how to take field theory limits of string loop amplitudes. using the mathematical formalism of tropical geometry, which in a nutshell tells you how a string worldsheet with holes becomes skinny, how a world line diagram with loops arises as a certain limit of the Riemann surfaces in string amplitudes. Yeah, and more recently, tropical geometry has been all over the place when I look into the audience. So we will, for instance, hear a series of summer school lectures next week by Micha Borinsky. More recently, tropical geometry has been extremely helpful to organize moduli spaces of Feynman graphs and to do more holistic calculations in QFT to work out features of the collections of graphs and not only the individual ones. Yeah, then we got to know the curve integral formalisms through two beautiful talks from yesterday and a variety of super recent papers done by many people in the room. And finally, there's intersection theory, which I guess it was Sebastian who brought it into physics, and I will speak about that in the first technical part of this review. All right. So here is an ambitious menu of topics I would love to discuss in all detail. Due to timing constraints, I have to be brief on some of them, but this is just the pipe dream, what I would be doing in case of unlimited time. So I hope we will jointly find a good path to give you a flavor of everything without boring you with too many details and without stressing the chairperson. Yeah, so the first topic to discuss in depth is Cavalier-Valentine and intersection theory at genus 1. So this is about the double copy line of ideas to get gravitational interactions for free once you have good control on the gauge theoretic ones. So this clearly comes from the fact that the gravity sector in string theories, coming from massless closed string excitations, has a nice relationship to the corresponding gauge theory excitations, which are sitting on the open string. And from textbook discussion of string theory 101, you see that the gravitational states are somewhat tensor products of color-stripped open string states. So spectrum-wise, this is close to obvious. But how does the double copy property of the spectrum uplift to double copy of string amplitudes? So this is far from obvious. So in particular, the integrals that you do in the process of evaluating an open or closed string amplitude, these integrals are far from obvious whether or not they preserve anything of double copy. So let's start with some simple examples where it does work. So here is the Cavalier-Valentine relation from '86, a seminal paper which also ignited a lot of activities in the field. KLT relations state that closed string tree-level amplitudes are indeed bilinears in open string tree amplitudes, color-ordered ones, decorated by trigonometric functions of the Mandelstams. Here and later, I used the Blackboard as an overflow platform when I couldn't squeeze a definition on my slides. So Mandelstam variables have an alpha prime, as you can see there. Okay, KLT relations tell you how to relate gauge gravity amplitudes, and mathematically speaking, they relate integrals. On the left, a surface integral over segments of the complex plane to contour integrals over a path in the complex plane. And this theme of relating those types of integrals, that is neatly formalized in intersection theory, an industry in mathematics that originates from the Japanese literature of the 90s, 80s or 90s. And intersection theory, in a nutshell, deals with a theory of integration for multivalued functions. So here's an example of a multivalued function of zi and zj, which you may wish to integrate in string theory. Of course, the discontinuities will be a bit disarmed in string theory, but this is a prototype integrand for intersection theory. And clearly, intersection theory has a beautiful way of deriving Cavalier-Valentine for you, even if you're not so good with contour deformations. So how does KLT hop out from intersection theory? So first of all, we need to generalize the notion of what an integration cycle is. So an integration cycle is not only a path from A to B, but in intersection theory, we speak of twisted cycle, which has some branch choice involved for the multivalued integrand. So I always need to state a branch choice along with the integration path to build a proper twisted cycle in twisted arm theory. So this is what the open string brings along for the color ordering, a twisted cycle. And here, this multivalued function is, of course, the famous Kober-Nielsen factor where all the alpha primes are sitting. Yeah, and then there is also rational functions which come out of CFT in string theory. And an intersection theorist would call them twisted co-cycles, rational functions. And in the case of a complex integral, you also deal with their complex conjugates, where for historic reasons we use a wedge instead of the overbar. Okay, so this is how the 4-point KLT looks like in intersection theory lingo. We look at pairings. Open string integrals are pairings of cycle and co-cycle, whereas closed string integrals have no notion of a cycle, but just a pairing of co-cycle and a complex conjugate. And there's a third pairing, which is not by itself a string amplitude. What if you do twisted cycle with another twisted cycle? And that's giving you a so-called twisted intersection number. And yeah, it's really important to have this multivalued admixture to the information in a twisted cycle. So these intersection numbers are not just 1 to 3, counting the conventional intersections, but they are trigonometric functions of the exponents or sign functions of Mandelstam invariance. Okay, with all of these definitions and formalisms, the 4-point KLT tells you how to relate these 3 classes of pairings. And for those who just come out from their quantum mechanics lecture will recognize this is a bit like a resolution of an identity. I mean, the suggestive bra and ket notation allows you to make it very intuitive why out of this pairing of co-cycles you have these bilinears in pairings that involve a cycle, and then there is an inverse intersection number in the middle. Okay, so 4 points I wanted to discuss in more depth. About higher points, let me just wave my hands and say that this is same, but with a higher dimensional homology and cohomology. So at n points, there is a basis dimension n-3 factorial, which is true both for the cycles and for the forms. So I don't think I need to bore you with further details about that. Let's fast forward to the KLT relation at n points rather than 4 points. It is still true that closed string amplitudes are bilinear in open string counterparts, and now there are some index manipulations involved. There is an inverse intersection matrix rather than an inverse intersection number. And you can once more read this formula as a resolution of identity. So once more, your intuition from the quantum mechanics course applies here, thanks to the hard work of the School of Mathematicians and Physicists developing all of that. So in a nutshell, tree-level KLT for closed string endpoint functions boil down to resolution of identity when you are equipped with this formalism of twisted intersection numbers. Yeah, and that genus 0 KLT is so robust, you can even generalize it further. Not just the final product of a closed string amplitude calculation, but also an intermediate step where only some of the mark points are integrated and others, like the variable x, is left for a later integration step. So here, intersection theory gives you bilinear relations for, well, some people know this as a single-valued hypergeometric function. And yeah, all of this business in inserting inverse intersection numbers, it goes through as if you had already finished the closed string calculation. So this is to set the stage for a KLT in intermediate steps in a string loop amplitude. You don't need to integrate all the moduli to expect such bilinear relations, but it's also okay if there are unintegrated moduli like this mark point x sitting around. Okay, so with this in mind, let's go straight into a genus 1 example, which firstly featured in the mathematics literature. So starting from the years 2008, 2009, mathematicians like Manu, Watanabe, Gasuani, Pirio, and Goto looked at specific genus 1 integrals that have common features with string amplitudes. So let's start talking about the geometry of these so-called Riemann-Wirtinger integrals. So this is about integration, not on the sphere, but now on a torus, the genus 1 worldsheet for a closed string 1-loop amplitude. And in a nice parametrization of a torus through a parallelogram, then there are 2 homology cycles called A and B, which go like from 0 to 1, or 0 to tau. These are definitely candidates to put into your twisted homology at genus 1. And as I was confessing to you, I enjoy having unintegrated mark points like x around. So let's also consider this as a candidate homology element, the cycle from 0 to x. So all of these are appealing choices to put into your integration cycle of Riemann-Wirtinger. But we are still in twisted homology. There is some multivalued function in here. So as a generalization of the x minus y to the power s from genus 0, we here have odd Riemann theta functions. So for those who don't know them by heart, the formula is on the board, at least for those who are lucky enough to sit close to the blackboard. So the only thing you really need to know about it is that it vanishes at the origin. So at small values of z, this goes like the z to the s factor you have seen before. So this is what mathematicians found natural as a twisted homology setting for genus 1. And what did they like as an integrand? What did mathematicians enjoy putting as a twisted cohomology? These are Kronecker-Eisenstein series that were mentioned in the talks of Lorenzo and Francisca. So practitioners of elliptic polylogarithms know this as a ratio of theta functions, which you can expand in terms of a bookkeeping variable eta to get some integration kernels G for elliptic polylogarithms, which were successfully used in various Feynman integral calculations. So this is what the Japanese authors from there and French authors found useful to put as a twisted co-cycle in there. And yeah, it is really true in the strict sense of twisted de Rham theory that you have a two-dimensional homology here and a two-dimensional cohomology. Like out of the three interesting cycles, there is one linear relation in between them. And this connects with string theory literature on monodromy relations on genus 1, which were intensely studied since 2016. Okay, so I think I've told you the basics about the meromorphic Riemann-Wirtinger integral, pairing twisted cycle with twisted co-cycle. And let's now look at a complex version thereof. Now we do a closed stringish integral over the entire torus, and the integrand is something like the absolute value square of the multivalued piece, and you're free to combine the left and right moving Kronecker-Eisenstein series. And here's the main result done by young people in the room, and a fourth young person who is currently not here, Carlos Rodriguez. So the result is a honest-to-God one-loop KLT relation to factorize this complex Riemann-Wirtinger integral into a bilinear of meromorphic ones here and their complex conjugates there. So in this, if you wish, warm-up example, which is not yet a string amplitude, but shares a lot of features with it, it is true literally that KLT is resolution of identity once more. So all of these phases here can be interpreted as the inverse of an intersection matrix. So this is a KLT relation that just hops out of the linear algebra once you have done the hard work to set up the twisted homology, cohomology, and the intersection number calculus. Okay, here this is in a case with a single integral and a single unintegrated point x. You can do more of these x's. More unintegrated passengers are okay, but it's an open problem to do this for double integral over additional z variables. So this is something I would suggest the entire community to work on. So far, so good. This was a warm-up example. Now, what does it have to do with actual genus 1 string amplitudes, this Riemann-Wirtinger integral? So let's take a brief look at how to formulate string theory one-loop amplitudes with an eye on double copy. So let's be careful what to do with the zero modes of the worldsheet field, because there is one of the zero modes called the loop momentum that intertwines left and right movers. So if you want to have double copy, better not integrate over the loop momentum too early on. In other words, this is the chiral splitting formulation for string loop amplitudes developed in the 80s, where you have to resist the temptation to integrate over the zero mode, and as a reward, the integrand is an honest-to-God double copy of a meromorphic chiral amplitude, representing the left movers, and a complex conjugate friend for the right movers. So if you want to have any chance to factorize post-integration, better use chiral splitting. Now, I have been rather sloppy about whether something lives on the torus or the universal cover thereof. You need to worry whether or not these chiral amplitudes are single-valued as you go around the homology cycles of the surface. And frankly, they're not. These chiral amplitudes have monodromies as you wind one of the marked points around the B cycle. But this is no problem. You can compensate these monodromies by shifting the loop momentum. I think we are doing this all the time, shifting the loop momentum, say, to deal with IBP relations or choose your favorite context, where you shift the loop momentum. So chiral splitting simply lives with a multi-valued function as long as you can compensate the monodromy with a loop momentum shift. And this is definitely the case within the CFT framework of chiral splitting. So let me be a little bit more specific what kind of gadgets are contained in the chiral amplitude. Here is once more a universal piece, the Kober-Nielsen factor. And let's look at the term highlighted in red, where the loop momentum contracts the external momenta, where you have something like an exponential of z, clearly a source of multivaluedness. And that red piece is a common feature with the Riemann-Wirtinger integral. So this is justifying my claim that the Riemann-Wirtinger is a useful warm-up before tackling the full-fledged string amplitude at one loop. So this factor here in the Riemann-Wirtinger Kober-Nielsen factor is the direct analog of this inner product of external and internal momenta. So even though I'm not sure if the mathematicians knew about loop momenta, they had the right nose that this is something you should put into the Kober-Nielsen factor. So on these grounds, I'm pretty confident that the work of the Brown group and Carlos Rodriguez, double copy on Riemann-Wirtinger, will have something important to teach for a double copy formula for actual closed string one-loop amplitudes. Okay, so this was a first flavor of one-loop double copy that I wanted to review. And here is a second one. Papers by Stefan Stieberger and Puriya Matslumi, who looked at the endpoint function of closed strings at one loop and who approached the torus integrals using contour deformations, who did a lot of complex analysis and combinatorically heroic contour deformations such that all the complex integrals become, at the end of the day, line integrals over an A cycle. Or you can also interpret it as boundary integral over a cylinder world sheet if you want to interpret this with open strings. So great news, as a result of all these contour deformations, you get the open string chiral amplitude in the right branch. So you can really say that locally you can find building blocks here that can be identified with the open string integrals in chiral splitting. And a minor disturbance to that is here, this factor in red, the so-called splitting function. So this is, in the end of the day, some combination of phases involving the loop momentum, which entangle the left and right moving variables psi and chi a little bit. So it's not that you can independently integrate the left and right moving open string coordinates, but you need to keep an eye on the splitting function. Okay, so this is one caveat. And another, maybe temporary artifact is that we have to assume the modular parameter to be purely imaginary. So on the long run, we would like to integrate over the keyhole region, the fundamental domain in red of SL2Z. And for the moment, this formula applies to the imaginary axis. Though I understand that Stefan is confident that this can soon be generalized to arbitrary tau, including a non-zero real part. Okay, and also this KLT formula fits into the theme of twisted de Rham theory. So as was shown in the paper most recently, this KLT kernel that I left a little bit generic here is in truth intersection numbers, or more precisely, the inverse of the intersection matrix adjusted to the twisted homology here. So Puriya and Stefan demonstrated that it's the intersection numbers in the sense of the mathematics work of Goto, which make the music here. Okay, so this is the state of affairs for one loop KLT for closed string amplitudes. There is a splitting phase, which obstruct a complete factorization, but which has physical interpretations. And it seems like from the level matching which it imposes, it really needs to be taken very serious as a physicality condition. Okay, and regardless on the splitting phase and the restriction to real part of tau, this KLT formula works really well in the tau to I infinity limit. So for instance, it was shown by Stefan that for alpha prime to 0, and by going to this boundary of moduli space, you recover an earlier KLT formula in field theory for the loop integrants in supergravity, as opposed to the string corrections. And also, you can alpha prime expand in this corner of moduli space and recover yet another KLT formula with co-authors in the room that concern one-loop matrix elements of higher mass dimension operators. But clearly, this KLT formula above here will go beyond in the sense that it attempts to also get the analytic contributions and low energy effective actions of one loop. So I'm quite looking forward to see what will come next on that front. Good. These were two pieces of one loop double copy, where a lot of attention was put on the integration contours, how you integrate the marked points on a genus 1 surface. I barely discussed what to do with the modular parameter tau that knows about the shape of the torus. So this question, where tau is sitting, this was, so to say, an opening line for a very impressive series of papers by Sebastian and Lorenz Eberhard. They did so much more than discussing tau contours. They went back to the basic question whether string amplitudes are convergent in their integral representation or whether they can be evaluated in the kinematic region where we want to evaluate them. So these papers pointed out and fixed very serious problems in that regard. And one way to describe the conundrum that got resolved is as follows. As Witten pointed out in this I epsilon paper, we have a discrepancy between Lorentzian spacetime and the Euclidean signature on the world sheet. This is not just some abstract bad mantra, but it has very concrete symptoms that make our lives hard, namely that various integrals don't converge in the region of S where you actually want to evaluate the amplitude. So you need sophisticated analytic continuation tools, and quite often they don't work globally in moduli space. And also, there is a headache with unitarity, namely the optical theorem tells you that loop amplitudes also in string theory need an imaginary part, but the way how we traditionally write string amplitudes, they are manifestly real. So something is going pretty south if we stick to the old-fashioned integration contours that you find in the textbooks, and one needs to work seriously on the integration contour for modular parameters. So these were the basic observations that started a series of papers of Lorenz and Sebastian. Like in one paper, they clarified how to do better. So I'm showing on the left the integration contours for open string at one loop, seen in the textbooks. So here is the combination of a cylinder diagram, namely the first imaginary line, and the Möbius strip in the second imaginary line. So by combining them appropriately such that the tadpole divergence cancels, you have a contour that looks like that. But this doesn't work if you want to respect unitarity. So instead, one should look at a contour like such, which has these little semicircles close to the real line. And this is really crucial because there are essential singularities to the integrand on the real axis. So it matters a lot from which tangent vector you walk into the real line. So this was the starting point, that contour deformation, for the reference here and later ones, where Lorenz and Sebastian taught us how to actually evaluate string amplitudes. And this is not just a formal prescription, but this is accessible to detailed evaluation and simplification methods. In particular for the imaginary part, it was shown that the contributions from these little circles already capture the imaginary part. And that is furthermore consistent with unitarity by comparing the honest-to-God evaluation of the integrals with what you would get from unitarity cuts in an infinite tower of massive states. And the real part is a little bit more work and is also an excursion into the artistics of the Rademacher contour. I think it will be rewarding if you have a chat about this with Sebastian. Okay, so there are concrete paths to do these evaluations. So all of these contour improvements are staying compatible with doing explicit calculations. And there were applications recently to high energy limit, matching with low energy expansions, and also some tree level spin-offs for any number of external legs. Good. Next topic. Everything so far was at genus 1. So on the remaining slides, I will proceed to arbitrary genus. So here I want to make contact with those in the room who enjoy doing integrals. I want to argue that string theory is a good laboratory to identify sensible integration kernels on higher genus Riemann surfaces. So we saw this already at genus 1, where the Kronecker-Eisenstein function was performing quite well in string theory exercises before it got popularized to get the elliptic polylogarithms for Feynman integrals. And also at higher genus, it turns out that by looking carefully on what the worldsheet has to offer, one gets a very solid guidance on how to set up higher genus polylogarithms. And by analogy with what the elliptic case was igniting as a crosstalk between fields, I very much hope that these results will also be relevant sooner or later to people working in one of those fields. Okay, so as I was saying, the idea is now to take the Kronecker-Eisenstein kernels to arbitrary genus. So there were the meromorphic ones that more people in the room are using. There are some single-valued counterparts that I will review shortly. And it's the single-valued versions which we generalize to arbitrary genus and work with Eric Doker and Martin Hidding. Okay, so once more, the Kronecker-Eisenstein series, but now together with a little phase that repairs the B-cycle monodromy and isn't quite meromorphic. So this is a generating function for the single-valued Kronecker-Eisenstein kernels. And okay, maybe they have appeared more in the string theory literature than elsewhere, but I understand that they were pretty valuable to identify a symbol alphabet for elliptic polylogs at rational points. And yeah, clearly in the closed string situation, these Fs were really the bread and butter to understand the zoo of non-holomorphic modular forms and single-valued elliptic polylogarithms. But okay, let's now come to the actual construction of the Fs, a second construction which generalizes beyond genus 1. So you could already wonder how these theta functions may generalize to higher genus. We do know what a higher genus theta function is, but to tell you the truth, I wouldn't know how to meaningfully generalize this generating function to higher genus. So instead, we look for an alternative way of writing the F kernels, and it is this alternative integral representation of the Fs which will generalize. The idea is to shift all the responsibility on the bosonic Green's function. So here, this object in red is the bosonic two-point function on the torus, which you can find in Polchinski or other textbooks. And by doing derivatives and convolutions of the Green's function, you have an alternative method to build up these Kronecker-Eisenstein kernels. And it is that convolution story which generalizes to higher genus. So the only leftover work is to give you a higher genus version of the bosonic two-point function. So this is an object known as the Arakelov-Green's function, which is first and foremost single-valued on two copies of the Riemann surface with points x and y. And you can define it from first principles using its Laplace equation, which tells you about a logarithmic singularity, and furthermore, a condition on the zero mode that vaguely it integrates to zero. Okay, so we will use this Arakelov-Green's function to construct higher genus variants of Kronecker-Eisenstein kernels. And the very last ingredient I need to introduce is the abelian differentials. So this is the generalization of dz, the unique abelian differential on the torus, to a higher genus case, where at genus G, you have a total of G abelian differentials. And one typically takes a basis choice where the A periods are Kronecker deltas, and then the B periods, they give you whatever they give you. So the B periods give you the period matrices that are the higher genus analog of the modular parameter tau. Okay, it's these abelian differentials and their complex conjugates which you need to do convolutions on higher genus. So here is a first example how a convolution gives you a higher genus F1 kernel. But wait, at genus 1, we only had a derivative of the Green's function. So here, higher genus has something like an add-on. There is an integral which we cannot have at genus 1 because the number of volume forms is too small. So we have the luxury at genus G to play with G square volume forms. And the traceless part of those is part of the F1 kernel. So it's really a 2 tensor simply because there is such a variety of volume forms. And going from F1 to F2 is again done by convolution in the same way as we did it at genus 1. And here I need to tell you which anti-holomorphic abelian differential you should use. And this is a source of indices. So for that reason, the higher genus Kronecker kernels have more and more indices, I1, I2, ... and all of them run from 1 all the way to the genus. So these are tensorial variants of the Kronecker-Eisenstein kernels. Okay, what makes us claim that they are good generalizations of Kronecker-Eisenstein? The reason that they pass some non-trivial stress tests is the following. We want to produce polylogarithms from them, functions that depend only on endpoints of integration paths. But it's tricky if you integrate non-meromorphic functions. Typically, you have path-dependent integrals. This is not a property you want for polylogs. We want to have homotopy invariant iterated integrals. And that is tied to having a flat connection, a Maurer-Cartan element J, which satisfy dj equal j wedge j. And the F kernels are fine-tuned to do that for you. The F kernels, they are stress tested by the fact that you can build a flat connection from them. So there are some generating function techniques to contract the indices into non-commutative generators A and B, never mind the details. But all this to say, the anti-holomorphic derivatives are exactly of the right type to obtain a flat connection. And that is your ticket to homotopy invariant iterated integrals, which we call higher genus polylogarithms. Okay, so this is one formulation to do higher genus polylogs. I will shortly review a meromorphic variant thereof. Maybe I'm not reviewing the string application for the sake of time, but I do want to discuss their functional identities. So let's go back all the way to genus 0 and wonder why the Goncharov polylogarithms are closing undertaking primitives. Why do you always succeed to integrate Goncharov polylogs times a rational function over the variable z? You succeed because of partial fraction. Whenever there is a degree 2 or higher polynomial downstairs, you can do partial fraction until the denominator is linear in z. So this is just to give some appreciation to partial fraction. It's structurally important to make the function space close under integration. And similar story at genus 1. You define polylogs by integrating over one factor of Kronecker-Eisenstein. But what if you have two z-dependent Kronecker-Eisenstein? That doesn't fit into the definition of elliptic polylogs. No matter whether you read Brown-Levin or other references, we have to get rid of the repeated z. And this just hops out of the standard Fay identities among theta functions. Here, this is a Fay identity in the literal sense. Now, how can we do this at higher genus? How to cope with a situation where we have a repeated appearance of the z's? So here is an example. Maybe you want to integrate that term with two instances of z, but this cannot be done with our polylogs in the generating function. So you have to remove that, and all the other terms have at most linear dependence on z. So this is an example of a higher genus Phi identity. No clue whether it coincides with Phi identities among theta functions, but we felt it is a good name to call them Phi by analogy with genus 1. So this is just to show off that it not only works at weight 2, but to arbitrary weight, and we are trying hard to finish it in the next 2 weeks. Okay, so these are Phi identities for the single-valued integration kernels at higher genus. And maybe some of you would prefer something meromorphic. So for those who prefer their elliptic polylogs to be fed with the G kernels rather than the F kernels, here is the meromorphic path towards Phi identities. I don't have the higher genus version of G with me, but they are implicitly in the work of Benjamin Enriquez, who defined meromorphic counterparts of the F tensors. Well, they are defined through their functional properties, most notably their monodromies. So these are exactly the right functional properties that we expect for higher genus GK kernels. So hence we are in vivid dialogue with Benjamin Enriquez and Federico Zerbini to get them explicitly in terms of the F kernels. And even if we can't write them down yet, these meromorphic Enriquez kernels, we believe that the Phi identities are exactly the same in between the single-valued kernels with explicit integral representations and the implicitly defined Enriquez kernel omega. Okay, so this is not the only way to build higher genus polylogs from a meromorphic connection. I should also highlight recent work by Enriquez and Zerbini, who have alternative ways to set up a meromorphic connection. It has to do with double poles and higher order poles, and you already heard from Lorenzo that this helps a lot on the elliptic curve to tolerate a double pole. Okay, I think I should go ahead wrapping up. So no time for the last chapter, but you can take a look at home if you're interested. So I was reporting on one-loop double copy formulae, continuations of KLT relations with a healthy symbiosis with intersection theory. You saw two flavors of that, one for the Riemann-Wirtinger integral, close to a string amplitude, and then the actual string amplitude calculation where you saw KLT-type formula with a splitting phase. So both approaches have their strengths and weaknesses, and I think we will all benefit from studying the two approaches in tandem. Then another topic was evaluation of string amplitudes at finite alpha prime. So I guess here Sebastian is your local expert to tell you more. And then I reported on recent progress on higher genus, where various ingredients of multi-loop string amplitudes, like Arakelov-Green's function, were useful to set up integration kernels for higher genus polylog. We did this using one flat connection using non-holomorphic kernels, single-valued ones, but in the near future, I hope we can connect with meromorphic flat connections in papers of Enriquez and Enriquez-Zerbini. Good, I should better stop here. Thanks a lot.
Thanks, Oliver, for a nice talk. Questions for Oliver? There are no questions. Maybe you can just say in a couple sentences what you had to skip.
Oh, I had to skip constructions of single-valued polylogs or various genus 1 counterparts thereof. So this goes under the mathematical name of single-valued periods. We need single-valued polylogs in multi-redshift kinematics. We need single-valued periods at genus 1 for closed string amplitudes. And they looked very different in the past. They have both their construction prescriptions, which worked eventually, but they looked so different, genus 0 versus genus 1. And our recent contribution was to make their formula look more similar. Or here are two generating functions where I didn't define the ingredients. But the upshot of these slides is that thanks to some recent work on so-called zeta generators, the formula look now very much alike. Doing single-valued periods as genus 1 became very closely related to single-valued period functions at genus 0. So I believe there is a genus-agnostic notion of zeta generators, certain derivations acting on fundamental groups, which allow us to deal with various genera at the same time.
Thanks. Last chance for a question. Okay, let's thank Oliver again then.